Hello everyone, welcome to this lecture on microprocessor systems and interfacing. My name is Dr. Vilayat Khan. I'm an assistant professor at ComScience University, Islamabad, VA campus. The topic of this lecture is different addressing modes used in uh, programming for the Intel family of microprocessors. In particular, mainly I'll focus on the addressing modes used in the 8086 microprocessor. These slides have been edited from these sources. These are the two sources from where I have edited these slides. Okay, so to begin with, a software program is a set of instructions written to solve a particular problem by the computer. Every application or program is a set of instructions. That set can be thousands or millions of lines of instructions that together solve a particular problem. For example, phone application in the mobile phone is a set of instructions that solves how to call a number or how to receive a call. And similarly, there are a number of other programs and applications that solves a particular problem by the computer. Then an instruction is an ingredient of a program. So an instruction is basically the direction which a microprocessor follows to execute a task or part of a task. So each program consists of multiple tasks, and each task is then performed by an instruction. An instruction is simply directions which a microprocessor follows to execute a task or a part of a task. So a programmer then write instructions, which is a set of directions given to the computer through these instructions, and these directions are assembled or properly ordered by the programmer, which are required for that particular problem to be solved by the computer. So program is made up different instructions, and to write instructions in particular order or particular syntax, different computer programming languages are used, just like natural languages, which define certain rules to write words and then sentences. Quite similarly, there are computer programming languages used to write different programs. Computer languages provide certain set of rules to follow, and the programmer must follow those set of rules or grammar to write computer programs. There are two types of languages, or in other words, there are two levels of computer programming languages. The first level is called high-level languages. In the high-level languages, the programming languages are more user-friendly, and it is easy to write programs, computer programs in the high-level languages. For example, Java, C++. These are MATLAB, for example. These are high-level languages. Mostly the instructions are given to the computers, but they are quite similar to the natural languages. And as they are quite similar or close in look or in syntax to natural languages, that's why they are easy for the programmers or for the human beings to understand and to remember. On the other hand, there are low-level languages. Low-level languages are very close to the machine, and unlike the high-level languages, low-level languages are difficult for the programmers to understand as compared to high-level languages. But low-level languages are close to the machine, and that's why it's easy for the machine to understand, but it's difficult for the programmers to write programs in the low-level languages. There are two types of low-level languages. One is machine language, and the other is assembly language. And in these two languages, machine language is the language that is very close to the machine, while assembly language is the language that is close to the user or to the programmer. So machine language is basically a sequence of bits. Binary bits or represent an instruction in the machine language. So each instruction is a sequence of binary bits, and then multiple sequences together form a program or a set of instructions. And these sequences of bits can be easily interpreted by the hardware components in the microprocessor, but they are very difficult to be written in proper sequence or order, very difficult to be remembered by the programmer. To facilitate this, assembly languages are used. So assembly languages are using English alphabets, mnemonics, and then obviously these English alphabets and mnemonics cannot be recognized by a computer machine. They can be remembered by the programmer because English alphabets are used, so they're easy to be remembered by the programmer or to be understood by the programmer, but they are difficult by the computer machines to be interpreted. To facilitate this or to automate this, these mnemonics are translated to machine language instructions using a program which is called the assembler. So the assembler is basically a compiler. They translate instructions written in the user-friendly assembly language in the form of English alphabets to binary bits in the machine language. And these binary bits are then interpreted or executed by the computer hardware. Addressing modes, as we just mentioned that computer programs are instructions or set of instructions, and each instruction performs a particular task or a subtask. In every task, there is some data where the instructions has to operate on. So every instruction, every program has to operate on a data, and that data must be stored somewhere. It must be stored in a register, or it must be stored in a memory location. So the different ways in which a source or destination operand is denoted in an instruction are known as addressing modes. So the different ways in which a source or destination operand is denoted or represented in an instruction are different addressing modes. To understand the different addressing modes, this is a simple assembly language instruction move. This instruction copies data from one location into the other, and this is assembly language instruction, so English alphabets are used. This is the name of the instruction or the operation code of the instruction, which simply is called opcode, MOV, that moves data. Here we have two operands, AX and BX. So these are the two operands, and this is the source operand, the 16-bit content from this source operand, which is basically a register in the microprocessor. So this is 16-bit content from this source register is moved in the direction of the arrow to this destination operand, which again is a register. So this move instruction moves 16-bit data from this source register BX to destination register AX. So we will be using this instruction to understand different addressing modes. But before going into different addressing modes, let me give you an analogy to understand why or what are the addressing modes in a computer or in the microprocessor instruction. So let's suppose we have to find a textbook or an item. Let's suppose that textbook is the microprocessor textbook, and one has to show or to tell the address of that book in different ways. So the address of the book can be represented or can be told or identified in different ways. For example, one way is to write shelf 1 main library University of XYZ, that is the address of the book. Another method can be to write the same address on a piece of paper and put it in the envelope and give that envelope to someone and write on the envelope address of the book. So that is another way to tell the address of the book. There can be a third way to tell someone that the librarian will tell you the address of the book. So just go to the librarian and librarian will tell you where the book is. There can be a fourth mode. I will tell my assistant who can tell who knows the address of the book. So my assistant knows the person who knows the address of the book. So just go to the assistant and he or she can tell you where the book is or who knows the address of the book. Mode 5, the address is mentioned in a letter in mailbox 2 somewhere in the university, and there can be a number of other addressing modes. So the address of the book can be provided through different ways, and these different ways are called the addressing modes. Just like that, the data is somewhere in the memory or somewhere in the registers. So to the address of the data can be represented in the instruction in different ways, and those different ways are used to represent the address of the data in the instruction are called the addressing modes. So there are 12 addressing modes. These 12 addressing modes can be combined to make little number of reduced number of addressing modes. They are named, they are given different names in different books and different tutorials. So if the number of addressing modes are reduced, then multiple addressing modes are combined into a single name. But in total, we have these addressing modes. These addressing modes are grouped. The first group, which is the group 1, addressing modes for register and immediate data. In this group, the addressing modes include register addressing mode and immediate addressing mode, and these addressing mode do not include memory addressing mode. The second group is called addressing modes for memory data. So in these addressing modes 3 to 8, data is accessed from the memory, and the memory address is represented or identified in these different ways, which make different memory addressing modes. Addressing modes for input and output ports. So they can be either direct I/O port addressing or indirect I/O port addressing. And then there is a port group that is relative addressing modes, which include just single addressing mode. And then finally there is an implied addressing mode. In this lecture, I will talk about addressing modes: base index addressing mode, string addressing mode, and direct or indirect I/O port addressing mode, relative and implied addressing mode. This discussion also includes discussion on addressing modes for memory data. Let me give a brief introduction of how the memory address is calculated. So in the 8086 microprocessor, the memory address is 20-bit address, and there are 20 address lines. But in 8086, the total memory is 1 megabytes, and the reason is that we have 20 address lines, so 2 raised to the power 20 is 1 megabytes of memory. So however, the largest register in 8086 is just 16-bit, so 16-bit is not sufficient to address 1 megabyte of memory. And to do that, physical address of the memory location has to be calculated. So physical address is the actual address of a byte in the memory, the value which goes out onto the address bus. Memory address is normally represented in this form, where there is a segment number colon, there is an offset part of the address. For example, this 89AB is the segment number, and the next value F012 is the offset value or offset address of this complete physical address. Each time a microprocessor wants to access memory location, it first takes the content of a segment register. If it is data segment, then it would go to the data segment register, and if it has to read instruction from the code segment, then that segment would be the code segment register. In any case, it goes to it takes the content of a segment register, shifts that and the content 16-bit content one hexadecimal place to the left. It is equivalent to multiplying it by 16 in decimal, and then with that shifted value, the offset, which is 16-bit offset shown here, is added with the shifted content of the segment, and then one gets 20-bit address. Here is an example. Let's suppose this is the 16-bit content of the segment register. This is the offset value. The 16-bit segment number is left shifted by appending 0 at the right hand side in the hexadecimal, or shifting one hexadecimal place to the left. That means a 0 is introduced at the right position here. So this 0 is introduced. This 0 is a hexadecimal digit. And then this offset value is added with this shifted segment number. This shifted segment number has now become a 20-bit value. So this 16-bit value is added with this, and we get the physical address or absolute address of the memory location like this. These are the addressing modes that are part of this lecture. So base plus index addressing mode. In base plus index addressing mode, the effective address is the address which is to be added with the starting address of the segment. So the effective address is computed from the sum of base register, for example, bx or base pointer, plus an index register, which can be source index or it can be destination index, and an 8-bit displacement. So in some books, this addressing mode is just base index addressing mode, but normally it is a good way to call it base plus index. It is easy to remember it. The effective address is calculated by adding a value in the base register. Base register can be a base register, or it can be a base pointer register, plus index register. It can be a source index, or it can be a destination index, plus an 8-bit displacement, sign extended displacement. So this instruction, the sum of these values in BX register, SI register, and this is an 8-bit displacement. These three values are added, and this would give us an effective address, which is again added with the left shifted segment number, and it will give us the physical address. So what this instruction does, move dx comma bx plus si plus 0h. This instruction moves 16-bit content from the data segment location addressed by this effective address and moves it to the dx register. And these are the operations to calculate the memory address. So first, this 8-bit displacement is sign extended to 16-bit because these values are 16-bit. So this value has to be sign extended. Sign extension means to extend it to 16-bit value while keeping the sign of the displacement in its place. So a 0a is sign extended by just adding or appending zeros at the left side. If it would be a negative number, then a 1 would be replicated here. So 0a is extended as 00a in hexadecimal. Then the effective address is calculated by adding the content of BX register represented here, plus the content of source index register here, plus the sign extended 8-bit displacement. So these three values will give us the effective address of the location. And then the base address is calculated as usual. The base address is currently the implicit segment to be accessed is the data, because the data is to be accessed. So if it would be an instruction, then it would be code segment, but here the data is being accessed, so the implicit segment is data segment, and the segment register will be obviously data segment register. So the content of data segment register is multiplied by 16 in decimal, or it is left shifted by one decimal hexadecimal digit, and this operation would give us the base address, just like we did in the an example in the previous slides. So the effective address and the base address are added to give the memory physical address. So we get the memory physical address, and then the 16-bit content from that memory location are moved to the DX register. As every location in the memory is just one single byte, so it can store just one byte of data. But by this operation we mean from the memory location just calculated here, a single byte is moved to the DL register using little endian format, and then the memory address, the physical address, is incremented by 1, and from the next higher location another byte is moved to the other part of the D register. So for simplicity, this is sometimes represented like this. So this is base plus index register. This BX register can be replaced with the base pointer. This SI register can be replaced with the DI, and this 8-bit displacement can be any 8-bit value. Then we have string addressing mode. This is employed in string operations to operate on string data. And string addressing, the effective address EA of source data is stored in the source index register, and the effective address of the destination of the data is stored in the destination index register. Segment register for calculating base address of the source data is data segment. Data segment is the source of the data, and the destination of the data in the string instruction is always extra segment. This can be better explained with an example. This instruction move S byte, so this moves each time an S is used with move instruction, that would mean a string instruction. So this is move instruction but move string instruction because of this S. So this move S as instruction would move a byte of string data from the data segment memory location addressed by the source index register to extra segment location addressed by the destination index register. And there are a number of operations are involved in this instruction, even though it's a simple instruction, and a number of addresses or effective addresses are involved, but they are implicit. They are not part of this instruction, but they are implicitly implemented by the hardware of the microprocessor. So for example, the source of the data is the data segment, and the effective address for the data segment is provided by the source index register. So the effective address is the source index register. The base address is calculated by left shifting the content of data segment register by 1 hexadecimal digit, and both the effective address and the base address are added. So this would give us the memory address of the source of the data. And similarly, memory address of the destination of the data is calculated as follows. So EA is the effective address for the extra segment, because extra segment is the destination segment. So this E represents extra segment, and that is the effective address is provided by the destination index register. The base address of the destination segment, which is the extra segment, is calculated by left shifting the content of extra segment by 1 hexadecimal place, 1 hexadecimal digit, just like we did with the base address for the destination segment. And similarly, the memory address for the destination segment, which is the extra segment, is calculated by adding the base address plus the effective address calculated here. So we just calculated the memory address or the physical address of the source of the data, and this is the physical address of the destination of the data. So this instruction moves a single byte of string data from this memory address calculated here to this memory address. And each time this instruction is executed, the source index content and the destination index register content are incremented by 1 or decremented by 1, and that is identified by the direction flag in the flags register. So if the direction flag register is 1, then it sets the auto decrement mode, and by auto decrement mode we mean that the content of source index register and the content of destination index register are decremented by 1 after this move instruction move s instruction is executed. And if the auto increment mode is set, that would mean the direction flag value is 0, and each time this instruction is executed, the content of these index registers are incremented by 1, and this mode is called auto increment mode. Then we have direct input and output port addressing. So in this mode of addressing, the port address of the input or output port is represented as part of the instruction by an 8-bit value. For example, here in direct port addressing mode, an 8-bit port address is directly specified in the instruction. It is part of the instruction. For example, this is an instruction NAL, 09H. So this instruction will read input data from the input port addressed by this port number, and will copy that the 8-bit data from this port to AL register. So let's suppose the operations involved are here. The port address, which is the address of the port from where the data is to be read, is here 09H. So 09H is the 8-bit port address from where the data is to be read into the AL register. So what happens, this operation will perform this read operation, will read 8-bit data from this port address here into the AL register. So content of port with address 09H is moved to AL register, and this is what happens in the N instruction. So in the direct input and output port addressing, the port address is directly specified as part of the instruction, while in the indirect IO port addressing, the address of the port address is indirectly provided through a register. For example, it's an output instruction. This output instruction moves a 16-bit value from the X register onto the output port represented with the port address DX. So this DX is a register that stores the 16-bit port output port address. So the address of the port is not directly specified as part of the instruction, but it is specified through a register, and that's why it's called indirect IO port addressing. So these are the operations that happens during the execution of this instruction. So the port address is the value in the DX register, and then this instruction will copy or will output the 16-bit value in the X register onto the output port represented with this port number. So content of X is moved to port whose address is specified by the DX register. Relative addressing mode. In this addressing mode, the effective address of a program instruction is specified relative to the instruction pointer by an 8-bit sign extended displacement. To understand this relative addressing mode, it's better to discuss it with an example. For example, JZ0AH, this instruction is jump F0 to this relative location. This is actually a displacement relative to the instruction pointer. So this instruction actually guides the microprocessor to jump to a location inside the code segment, and that location is relative to the current content of the instruction pointer. So currently instruction pointer points to a location next to this instruction, but this instruction tells the microprocessor to instead jump to a relative location, and this 0A is a displacement which is to be added with the instruction pointer content, and that would be the new address where to jump. So these are the operations involved in this instruction execution. So first, this displacement, 8-bit displacement, is sign extended, just like we did before. So 0A is extended to 16-bit value, as this is positive, so just zeros are appended at the left hand side. So we get sign extended 16-bit value now. Now jump F0, so this is a conditional jump. If the 0 flag is 1, then the jump will happen and these operations will happen. Otherwise, if Z flag is not 1, then the jump will not happen, and this the address calculation will not be needed. So let's assume that Z flag is 1, so the jump will happen. Then these calculations will happen, these operations will happen. So this is the 8-bit sign extended displacement. This is added with the current content of the instruction pointer, so that's why it's relative to the instruction pointer. So the effective address, the new address of the jump, is the new address of the jump, or the new address from where the microprocessor has to execute instruction, is the as the effective address, this calculated here. So this sign extended value is added with the instruction pointer, and we will get the effective address. And the base address is the calculated by left shifting the content of the segment register by 1 hexadecimal digit, or by multiplying 16 in the decimal value. So this would give us the base address of the code segment, that is the address from where the code segment begins. And this is the effective address, so both addresses are added to get the memory address, memory physical address. So F is 1, then the program control jumps to a new address calculated above. So the new instructions are executed from this new address, from this memory address. And if Z flag is 0, then next instruction of the program is executed. Okay, so this is relative addressing, and there are a number of other jump instruction, and most of them involve this relative addressing. And finally, we have the implied addressing mode. In this addressing mode, the relative address is implicitly provided through the hardware of the microprocessor. So the address is not part of the instruction. It is implicitly, or it is hidden in the instruction. So instructions using this mode have no operands. The instruction itself will specify the data to be operated by the instruction. And the example, there is an instruction that clears the carry flag. So the microprocessor, when microprocessor executes this instruction, it knows where the data is. So the data to operate on is in the flags register, the C bit, the carry bit in the flags register, and this instruction will just clear that carry bit of the flags register, and this is implicitly implemented in the hardware of the microprocessor, and programmer does not need to provide that address as part of the instruction or through other modes of addressing modes. The programmer just has to write the name of the instruction and the address of the operand, which in this case is the carry flag, is implicitly provided. So it clears the carry flag to 0, and the operand is not provided, but it is implicitly there. So this is implied addressing, and there is no operand involved in this instruction. Okay, so these are the addressing modes. If there is any problem, query, question while watching this lecture, please keep a note of those queries, write them on a piece of paper, and you can ask those questions or queries when during the online session. Thank you.